All right. So we went through all the patterns here. We came up with the true-false statements yesterday. Remind me again what we did with those false statements yesterday. Okay, we said, what if we could redraw the three sections in that Venn diagram to make that statement true? And you know, it wasn't the most difficult thing in the world, but I thought we might have a little trouble with it. You guys did a great job with that yesterday, so I was really pleased to see that. So that said, the explorations we looked at today, I'd like to get through these last 3 pages of notes here, and then I'll send out a short assignment. And you know, you guys have worked pretty hard this week, and today being Thursday, why don't you guys just plan on taking Friday off? Have a 3-day weekend. Fair deal? Fair deal. And you know what? Just go for about 29 days this month. Don't go 31. Just go 29 days this month, okay? Okay. Okay. All right, here we go. Hey, guys, back on this idea of inductive reasoning right here. Example 1 says describing a visual pattern. And right here it says describe how to sketch the 5th figure in the pattern. I'm not going to make you sketch that figure, but guys, I want you to understand a couple things here. Number 1, can you make a statement about what to do in terms of sketching the 5th pattern? What's happening here from picture 1 to picture 2 to picture 3 to picture 4?
Putting more squares on the ends.
Okay, so when you say ends, do you mean like the corners, if you will? Okay, so if this was kind of like a box shape, you'd say in the corners. So to draw the 5th figure, picture 5, in your own words, Gavin, what do you think you want to do here? You said add a block to the corners, right? So basically you're saying if this is picture 1, this is picture 2, picture 3, picture 4. If I understand you correctly, you're saying to get to picture 2, you got to take picture 1 and add these corners right here. Is that what you're saying right there? Okay, so to get to picture 5, which picture are we going to have to adjust? Okay, so you're going to add how many blocks?
4.
Technically 4. So could I write down add a block to all 4 corners of picture 4? Would that be okay, guys? Okay, add a block to all 4 corners of picture 4. Now guys, as we went through this right here, did we just do something based on fact, or did we kind of see a pattern evolving here? It's a pattern. So when we made this statement right here, is that statement that we did deductively or inductively? No. Inductively. Okay, did that inductively. So that'd be some kind of inductive reasoning right there. Okay, some kind of inductive reasoning. All right, so very good. Very good. All right. Second example here then talks about making a conjecture. Make a statement based on. Make a statement based on a pattern that you see, or make a conjecture or a hypothesis, if you will. Okay. So in example 2, guys, this is where we start getting into this idea of saying, I'm going to make a statement, but then I need to have some kind of a justification. You need to come up with some kind of a statement that proves or disproves your conjecture. Either proves it true or proves it false. So in example 2 right here, guys, it says make and test a conjecture about the product of a negative integer and a positive integer. Okay? This word product, what operation are we discussing? Multiplication. So we obviously know that a negative times a positive is what kind of a number? Negative. So that would be a conjecture we're going to make. You know what? We're going to say this. Conjecture this. Conjecture this. A negative times a positive. A negative times a positive is what? Is negative. Good. Okay. What are the orders that you can multiply a negative and a positive? First number could be what? First number could be positive, right? Which means the second one would have to be negative, or vice versa. We could take a negative times a positive here. So Check this out. Let's just test this. This is the test we're going to do to maybe put some clarification to this, or some justification, if you will. Let's say maybe, how about 6 times -4, kiddos? What's that equal? -24. With that test right there, is my conjecture true or false? When I took a positive times a negative, did we get a negative product? You bet we did. Okay. Maybe I switch the order on this. Maybe I say, how about this test? How about, say, -2 times 4? What's that equal, kiddos? -8. Well, there's a test. You've done that. You've taken a negative number times a positive number. Okay. What if you take a positive m times a negative n? First of all, is your product going to be positive or negative? Negative. So it'd be -m times what? It'd be -m times n, right? Be -m times n. Is that conjecture true or false? Based on the tests I've shown you, is that conjecture true or false? It's what? It's true. You bet it is. It's true. Good. All right. So conjectures can be true, but you've got to prove it. Okay? Now, in example 3, I love example 3. This is a big word. Counterexample. Maybe you guys, all right, so I guess you guys, maybe MMA fighting is the type of thing to watch. Any of you guys watch that stuff at all? Sometimes? Okay. They might say somebody hits somebody and then the other guy counters with something. What's the word counter mean? I countered with a right after I got jacked with a left. What's that mean?
You got punched with the left hand.
Well, I got punched, but I countered with a right. What's that mean?
You like came back with it.
I came back with him. I had an answer for him, right? I had something for him, okay? Hit me once, shame on you. Hit me twice, I counter twice on you. Ooh, that's good, man.
Never heard that.
All right. Hey, a student makes a conjecture about absolute values. We need to come up with a counterexample. What a counterexample is something. Here's the deal. Here's the deal. You might say, today is Wednesday. And I might come back with a counterexample and say, no, it's Thursday. And I can get a calendar out and show you that it's Thursday, right? Okay? That'd be a way of proving you right or wrong.
Right.
Ah,
Wrong.
I'm proving you wrong, okay? Counterexample is something that we use to disprove statements. So here's a statement that they put up here, guys. It says a student makes a conjecture about absolute values. Okay, remind me again, absolute values. What's it mean to be absolute value? How about a question? Absolute value of 10, what is that? 10. Absolute value of -16, what is that?
16.
Okay, so absolute values are going to, for the most part, be positive. They represent the distance from 0. Okay? So they make this conjecture right here. We need to find a counterexample to disprove this student's conjecture. Student says this: the absolute value of the sum of two numbers, sum meaning what operation? Addition is equal to the sum of two numbers. So they're saying I can take two numbers, add them up, and get a number, and that'll be the same as taking the same two numbers, adding them up, and then taking the absolute value of that, all right? So let's check this out. Here's one example. All right, guys, let's do this. What's 6 plus 2? 8. So how about the absolute value? And I kind of messed this up, I think, a little bit yesterday. Absolute value of 6 plus 2. What would that be? 8. Let's see. Is that statement true or false the way I've come up with this? That's true. Conjecture is true, right? Now remember, in order for something to be true, that statement must be true part of the time or all the time. I've only provided one example here. But is the example supporting the conjecture, or is it disproving it right now? Supports it. Okay? Let's try another example. How about this? Okay, I got this. I got this. I got this. I got this.
Do you have it?
I've got it.
Do you?
What if we did this? Let's see, 6 plus -3. What's that equal, kiddos? 3. Okay, well, inside of parentheses or inside of the brackets for absolute value, same exact thing. So isn't this really the absolute value of 3 also? Which would still be what? 3. Does that statement support or disprove your conjecture? It supports it again. All right? Here's where things get maybe a little tricky. What if I did this? This is an interesting one. Oops, I didn't want to do that. I messed that up completely. You know what? Here, just put a negative with both of them. We'll do this.
Students going on Mrs. Zondo's field trip, please report to the office. Students going on Mrs. Zondo's field trip, please report to the office.
Okay, I'm going to go -4 plus -10. What's -4 plus -10? -14. Okay, so inside here, wouldn't that be -14 as well? But then when you decide to take the absolute value of what's inside there, what are you going to get? 14. Okay. How about that example right there? Does that support that conjecture, or does that disprove it right there? It just disproves it right there. And we would say, you know what? These values, -4 and -10, when added is -14, but when you do the absolute value of that sum, it is +14. Therefore, I could say the values of -4 and -10 are considered a, what, didn't want to cross it out, I wanted to underline that. They're considered a what? What's the word? What word did I underline here? This is a counterexample to the conjecture. Those two numbers right there completely disprove that person's statement about the sum of numbers and the sum of the absolute values of those numbers. That one example completely disproves it. So is that statement true some of the time, like we had in red, or is it true all of the time? Some of the time. And anytime we take a statement in general to be true some of the time, it's actually considered to be what kind of a statement then? False. Okay, because -4 and -10 are considered to be I'm going to try and squeeze it in here. I countered with that example right there. Okay? And you know what? I just made that conjecture tap out. Okay? Channeling my inner Ronda Rousey today. Conjecture ain't got nothing on me, right? Am I right?
Did you hear what Ronda Rousey said on?
I did. That just shocked me. You know what? I think she's kind of a troubled individual, and I kind of feel sorry for her, honestly. I used to feel sorry for the people she was beating on, but now I kind of.
She
Didn't
said
she get
that
knocked out?
after she lost that one.
Yeah.
Okay. Everybody cool with this page? Holly Holm, I think it was. Okay, so we've been looking at a lot of things that involve patterns so far, which, that's great. It's considered inductive reasoning. So I want to go ahead now and maybe focus a little bit more on deductive reasoning. You know what? Reasoning based on facts or logic or definition. And you don't need to write that down. I just want to kind of give you an idea of what we're talking about. We're basing stuff on facts or logics or definitions. Okay? There's going to be two laws that come in here with deductive reasoning. There's going to be what's called the law of detachment and the law of syllogism that allow us to make some reasoning based on facts or make some conjectures based on facts. And so I guess the first law of logic that relates to deductive reasoning is called this law right here. It's called the law of detachment. All right? I have a volunteer that would read what that definition is for me. Thanks, Carson.
If the hypothesis of a true conditional statement is true, then the conclusion is also true.
Okay, so if the hypothesis of a true conditional statement, so the if part is true and the then part is true, then we can apply law of detachment. So example 4 is an example of law of detachment. Here it is. Example 4 using law of detachment. It says if a figure is a square, then it's considered a what? Okay, so let me draw this quickly here. Hey, you know what? I can do it right here. Give me a second. looks like a square, doesn't it? And this looks like a rectangle, doesn't it? Right? Okay. Okay. Rectangle right here, guys. Here's the deal. A rectangle. What's true about all the angles in a rectangle? 90 degrees, right? Are all the angles of a square 90 degrees? Second question. What's true about the length of opposite sides here? The top and the bottom, are they equal in length? How about the top and the bottom? Are they equal in length?
Yeah.
How about the left and right? Are they equal in length?
Yeah.
So how about the left and right here? Are they equal in length?
Yeah.
So is it possible to say, you know what, even though we would say specifically this is a square, we could also call this a what? Rectangle. Could I call this rectangle over here on the right a square? No, I couldn't. So what I can say is this, I can say all squares are rectangles, but not all rectangles are what? Squares. The way they set this up is the following. They say, hey, if a figure is a square, so assume this. So they're saying if you have a square, then you also have a what? Rectangle. So any square that you have, you know you have a rectangle as well, right? Okay. Right here it says, if a figure is a square, then it's a rectangle. You know that quadrilateral ABCD is a what, kiddos? What's it say?
Square.
It's a square. Using law of detachment, what statement can you make? Well, I just said, if you have a square, you have a what?
Rectangle.
And I just said ABCD is a square, so what else can you say about ABCD?
Rectangle.
By law of detachment, it's also a
Rectangle.
rectangle.
Yeah, that hurt his hand.
So ABCD, I have to file for workman's comp after I hit that table.
Told you.
ABCD is a what? Yeah. And what law is that again? Listen to what I say here. If a dog is a puppy, then it has 4 legs. If a dog is a puppy, then it has 4 legs. At home, the name of my puppy is Milo. Milo is a puppy. What can you conclude about Milo?
Dog.
Milo has 4 legs, right?
What if it lost a leg?
It won't lose a leg. Well, the way he's acting right now, I might take a leg. Okay. I'm not mean. I'm just fair. Okay? You choose on my legs?
So you're gonna chew on his?
Eye for an eye, buddy. Probably tastes like chicken.
I know someone who has a.
Oh, come on. Every time that you go and order something that you don't know that you've had before, you say, tastes like chicken, right? Everybody says that. Tastes like.
We're talking about a household pet.
Oh, that.
That's
I wouldn't do that to
different.
Miles. Miles my buddy.
You
I know
just said you chew
someone
off
who
his
has
leg though, so.
I know someone who has a cat that
It was a
has only has 3 legs, so they
Oh
call
no.
They call it Legolas.
Legless?
Legolas, like Nicholas, but Legolas.
I like it.
Just Legolas.
Okay, so law of detachment. Are you okay with that? If something, then something, and then they say, okay, all of a sudden, here's a quadrilateral ABCD, it's a square. And by this rule right up here, said all squares are a rectangle. Okay, I think the one most important thing in the notes today is this law of syllogism. Okay, I want to talk about this and hit this hard. This is kind of difficult. Okay, well, it's not difficult. It's just going to be very foreign to you. I want you to make sure you understand what it is you're getting yourself into here, okay? All right, law of syllogism says this.
Wait, I have a question.
Yeah.
How come B and C have a line through on your A?
I was just underlining them.
Oh,
Oh, this here?
yeah.
I don't know. It just connected. I must not have picked it up. So it's just.
I wasn't sure if it.
Yeah, no, that was just a mistake on my part. Okay, law of syllogism. Here we go. I think the easiest way to write the law of syllogism is like this. I'm going to say the following. If. Okay, here we go. I'm going to put 2 lines here. If P implies Q. Okay, again, P and Q are going to be statements. And then also if Q implies R. You know what? I'm going to stack it. I think it would be better to do it this way. Okay, so how many conditionals have I given you as a hypothesis right here, right after the word if? How many conditionals are here? Okay, then watch what happens here. I think the best way I can explain it is this. The best way I can explain it is this. Guys, in those two conditionals, what letter appears in both conditionals? Q. Does Q occur in two different spots, meaning one at the end and one at the beginning? Okay. What you're looking for in law of syllogism is implications where you have a variable that's the same, but that variable has to occur at the end of one and at the beginning of the other. End of one at the beginning of the other. So I'm going to kind of circle the Q right here because that's kind of important to us. That's the variable that appears in both implications, and it's also at the end of one and at the beginning of the other. Would you guys agree with that?
Yeah.
Okay, this implies then P would imply R. Okay, P would imply R. I want to show you what's really happening here. Let me know that you've got that rule written down first, the law of syllogism. Do you have the rule written down? Let me show you why this works. We said P implies Q, and Q implies R, then that must mean that P implies R, right? Let me show you how I'm talking about this, guys. What did P imply again, guys?
Q.
Q. If I could take this right down here and pull it down here, does P imply Q just in that first part right here now?
Yes.
But then Q implies what? So basically, to go from P to Q, then Q would go to R. You can basically bypass Q and go straight from P to what? R. Does that make sense to you?
Yes.
Okay, so let me show you this here. Let me show you a great example of what law of syllogism is. All right? Law of syllogism example 5. A very important example here. Okay. It says, if possible, use the law of syllogism to write a new conditional statement that follows the pair of true statements. Okay, we have two if-then statements in here. Okay, so let's look at letter A. First of all, when you're using law of syllogism, I would say find the words if and then. Find the words if and then. So in this example right here, it says, if soccer practice is what? Canceled. Okay? So we're going to say if soccer practice is canceled. I'm going to go ahead and call that part of the statement P. All right? And it doesn't matter what you call it. But you have a part of the statement that says if soccer practice is canceled. Then what's going to happen, guys?
Go to the mall.
Then you can go to the mall. So the part right after then I'm going to put in parentheses like this. And I'm going to call that probably what? Q. Okay, so the first sentence is P implies Q. I've assigned soccer practice is canceled to P. I've assigned then you get to go to the mall as Q. Now there's another sentence here, guys. It says if it is what?
Raining.
If it is raining. Okay, let's see. Another hypothesis. If it's raining today. Let's see. Did the first sentence talk about rain anywhere?
No.
Not at all. So I can't call that if it's raining P, and I can't call it Q, so maybe we call it what?
R.
How about we call it R? Then what, guys? Soccer practice is canceled. Ooh. Didn't we have a statement there that said soccer practice is canceled somewhere in here already? And what letter did we call that? Letter P. So what am I going to call this part down here again? Okay, quick question for you. In the second sentence, if it is raining today, then soccer practice is canceled. We would say R implies what now, guys? R implies P. Okay, first question. I want to know if I can even use law of syllogism. So the first question would be, is there a variable that shows up in both implications? What is that variable? P does, all right. Second question, is that P at the beginning of one statement and at the end of another?
Yes.
Okay, so right here. So what this would mean then, guys, is the following. If we want to rewrite a new conditional statement using law of syllogism, if R implies P, like this right here, R would imply P, and then P implies Q, what can you say about the R and Q then? We can bypass what letter and say R implies what?
Q.
So this means that R implies Q. So we're saying if statement R, then statement Q by law of syllogism. So here's what this would really say. These two conditionals put together as one by law of syllogism would say the following. It says if. All right, what's statement R again? If it is what? What did we assign R to be? If it is raining today, right? Then what? Okay, careful. We're going R to Q by law of syllogism. Then you can go to the mall. Okay, and let me kind of walk you through this logically. Basically, if it's raining, then what's going to happen to soccer practice? And since soccer practice is canceled, you're going to the mall. So it's saying, if it's raining, we're not even going to talk about soccer practice. We're just going to assume we don't even need to talk about that anymore. Because if it's raining, soccer practice is automatically canceled, right? So I can simply say if it's raining, then you can go to the mall, right? Under the assumption that what's going to get practice or canceled? Soccer practice. Okay. All right. So let's try another one. Put this one in red. It says if a figure is a rectangle. So I'm going to go ahead and set it up the same way. If a figure is a rectangle. So a figure is a rectangle. What letter do you think I'm going to call that first? P. Then all interior angles are right angles. What do you think I'm going to call that? Q. So the first sentence, P implies Q, right? The next one says if a figure is a what? Square. So that's different, isn't it? R. Then all interior angles are right angles. What letter is that going to be?
Q.
So in this one right here, R implies Q, right? First question. Can we use law of syllogism to come up with another conditional? Well, is there a variable that appears in both implications?
Yes.
What is that variable?
Q.
What's the problem the way Q is positioned this time?
Opposites.
They're both at the end, right?
Yeah.
So therefore, can I use law of syllogism here?
No.
I can't. The only time I can use it is if the variable exists in both implications. One's at the beginning and one is at the end. That's good. Here they're both at the end. That's bad. So what I'm going to say is, from the following example, if possible, can you use the law of syllogism to write new conditional statements that follows the initial pair? You're just going to say not possible here. Okay? This one is not possible. That is not possible. Okay, so if you're using law of syllogism, you're saying something implies something, two implications, looking for implications that are the same. In order to apply law of syllogism, that same implication has to be at the beginning of one sentence and at the end of the other. Okay? So you understand the difference between A and B? Are you with me on that? Okay. So I really believe that that's probably the most important kind of thing that you're going to see today in the assignments. So that being said, let's roll on ahead here. So the last page of notes, we'll get this done, and I'll get that assignment out to you, and we'll call it good for the week, okay? Anybody need more time with that page? Everybody have what they need? Good? All right. Next example then, using inductive and deductive reasoning. Guys, the table shows the sum of measures of the interior angles in various polygons, okay? Let's fill this table out. Guys, right here, triangle. How many sides? 3. You guys know the sum of the measures of the angles in a triangle add up to how many degrees? 180. Okay? Forget the pattern for now. Okay? Quadrilateral, how many sides? 4. Now a quadrilateral, 4-sided figure, I could cut diagonally into how many triangles? 2. So it'd be 360, right? How about a pentagon? Pentagon, 1, 2, 3, you don't need to draw these, 4, 5. This can be divided into 1. How many triangles can I divide a pentagon into? 3. Somebody do 180 times 3 for me to know some of the angles are there.
5, 4.
I'm going to write this down. Well, 540 degrees, okay? How about a hexagon? How many sides?
6.
Okay, I'm going to talk about my pattern real quickly, guys. This pattern right here for the angles right here, this was really 180 times 1, wasn't it? This was 180 times, how many triangles were there in a quadrilateral? Times 2. This is 180 times 3. What do you think this is going to be for a 6-sided figure? 180 times 4. Okay. Run 180 times 4. How many degrees do you get for the interior angles of a hexagon? Okay. I'm going to put a question up here. I'm going to pose a question for you. All right? Let's say I got to a shape that had 14 sides. And I wanted to know the number of degrees that the interior angles add up to for a 14-sided figure. Anybody have a thought on what they would do to find the number of degrees in a 14-sided figure based on what we've done up here already? Anybody have a thought? Miller, what do you think?
14 minus 2, which would be 12, and then take that times 180.
Why'd you subtract 2 from 14?
Because that's pretty much what's happening with
That's
number
the
of
pattern,
sides.
isn't it? Right here, 3 minus 2 is what value, guys? 1. 4 minus 2 is what value? 5 minus 2 is what value?
3.
6 minus 2 is what value?
4.
So does it stand to reason that down here to get the angle measures of a 14-sided figure, you would go 180 times 12, 2 less than the number of sides? Makes sense, right? So here's the deal. They're going to ask you to form a conjecture about the number of degrees in an n-sided figure. So I'm going to say this again right here. You took the number of sides minus what? Times how many degrees? Let's see. Number of sides minus 2 times 180. Okay, you're exactly right. How do you come up with the number of degrees in an n-sided figure where n represents the number of sides? So here's a nice little formula. We just inductively reasoned. We looked at a bunch of patterns here, didn't we? And we came up with this idea that, hey, number of degrees in a polygon, is the following. Okay, what do we do with the number of sides first? We took the number of sides minus how much? 2. So we're going to say n minus 2. And then we multiplied that by what? 180. That pattern proves it. So if I wanted to know how many degrees were in a 65-sided figure, I don't know why you would want to know that. Saw a thing on Facebook last night that kind of ticked me off. Want to hear about it?
Yeah.
Now that I'm on the subject. Something about how schools don't teach taxes and how to vote and blah, 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 which I disagree with. I think they do. But then they said, sure glad I know the Pythagorean theorem. And I wanted to write back, I've never heard of a student getting scholarships about knowing how to do taxes or knowing how to vote ever in my life either. So, just saying. Okay. Anyway,
You should have typed that.
onward and upward. No, I didn't want to start anything.
What were they going to say back to that?
It's a good question. Probably nothing.
You should have just been like, you should have typed it and been like, oh, boom roast.
It gets me going. Anyway, if I want to know a 65-sided figure, some of the angles in a 65-sided figure, you take 65 minus what? 2, and then times that by what?
180.
Does formula make sense to you?
Yeah.
You want to know what? You had no idea that that formula even existed. That's an actual formula. You had no idea that formula existed until we started looking at patterns. This formula is formed by inductive reasoning. Okay? Inductive reasoning. I can't tell you guys how much I think that when you go through stuff like this, thinking logically or having to reason or stuff or having to prove stuff like this, I tell you what, that makes you If you can understand this stuff, that makes you pretty bright in my book. Okay? That makes you pretty bright in my book. All right, last example. Let's run through these. Decide whether the reasoning is deductive reasoning or inductive reasoning, and kind of explain it to me. So in letter A, it says in the sum of the digits, of a number is divisible by 3, then the number is divisible by 3. The sum of the digits of the number 147 is 12, meaning that 1 plus 4 is what value? 1 plus 4 is 5. 5 plus 7 is 12. So the number 147 is divisible by 3. Okay? So they're kind of giving you a fact. They're saying, hey, if you add all the numbers up and it's divisible by 3, then the original number is divisible by 3. They give you a fact right there, don't they? They gave you a fact. So what kind of reasoning is that? Deductive. Okay? All right? Letter B, finally. Each time you forget to do your math homework, your parents take away your phone privileges for a day. So the next time you forget to do your math homework, you will lose your phone privileges. Each time. Each time. Are we talking about one time or multiple times probably? Over time. Each time. Each time. Each time. Each happens over and over and over and over and over again, right? Is that a fact or is that a pattern? That's a pattern. So what kind of reasoning are you using there? Inductive here. Okay? Inductive. Kiddos, what questions have you got over the notes? This is a tough section. I really believe it is, but man, I tell you what, like I said, this is the first time I've taught this type of stuff. Going okay? Feeling okay about it? Okay, I was a bit nervous about how this would go, but I think we've got a lot of good examples here in this section of notes to help you be successful. You guys feel okay about it? Any questions about it? Okay, I'm going to shut the recorder down here, and I'm going to